Now we're going to talk about polynomial functions, and it's graphs. So we just basically we just touch it and understand some concepts. So poly means more, multiple, right? Polynomial functions and their graphs. Not too much, not too complicated. Now, quick review, linear function. Linear function looks like this. Looks like f of x equals ax plus b, or mx plus b. Okay, and then let me just use mx plus b. Okay, so that's a linear function. The quadratic function f of x looks like this. F of x equals ax squared plus bx plus c, right? So this is the first degree, or just the x term, and this is the x squared term, a quadratic. What about if this power gets higher and higher? And let me write you this. F of x equals, I have something about x to the nth power, okay, and I have something about just one lower than that, and so on and so forth. At the end, I also have x squared and x and a constant. So how do I write? See, here is how you write the coefficient of the square term. You use a, you use b, you use c. But here we have so many terms. How many? We might have n plus 1 terms, because there's a number, a pure number at the end. So instead of using a, b, c, d, you're going to finish up all the letters quickly. We are going to do this. We're going to use an. It's just a little notation. So an means that's a coefficient of the x to the nth power term. And then plus a n minus 1. And of course, you're going to plus. The next one will be a n minus 2 and x to the n minus 2 power. And all the way to this will be a2, and this will be a1, and then the last number is a0. So we write things like this. This is a polynomial function. So instead of linear, quadratic, we go higher. And linear and the quadratic function are two simplest examples of the polynomial function. They are also polynomial functions. Now, some concepts, this n. When an is not 0, that means there's a number, there's a coefficient, it's a non-zero coefficient for the highest degree term. So this n, the highest power, this n, we call that a degree. Okay, and then this an, we call this as a leading coefficient. Okay, and each one, an times x to the n, an minus 1 times n, x to the n minus 1. So each one is called a term. Okay, and the last one, this a0, we call that constant term. Constant term. Okay, it's just a number without x. All right, now once you're given a function looks like this, there's something that you can tell. We call that end behavior of the graph. End behavior. And behavior of a function, a polynomial. Polynomial function. What does that mean? Okay. And the behavior of the polynomial function. We don't care about how many terms totally we have. We don't care about the constant term, because when we talk about an end behavior, which means when this x goes really, really big on the positive side, or goes really, really, really far away to the negative side. So which means when the x goes to positive infinity and a negative infinity. And then what will be the behavior of it? And then we only care about this n and an. Okay, so let me say this. if n is odd. That means when n is 1, 3, 5, 7, right? That's an odd number. So when n is odd and you have an positive. Okay, so think about this. If you have a positive number here and n is an odd number, so when x becomes positive infinity and when x becomes negative infinity, to see what happened. All right. Now when x becomes a huge number, then that's going to be, here is going to be a huge number to nth power. It's going to be huge, and then you're going to multiply by a positive number. So this one, that means when x goes up, so you're going to have something look like this. It goes huge. Okay. So when x is a negative number, this is the tricky part. When x is a negative huge number, let's say negative a million or maybe a billion, and n is odd. Let's say n is a 3. So negative, very, very negative number to the third power. So negative, 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 you get a negative, right? And it's going to be a large value. Well, in terms of the absolute value, it's going to be big. And you have an is a positive, so you're not changing the sign, so it becomes this. So what it says is when x goes to the left, and then the function or the graph of this function will drop. Okay, so it shows. This is called the end behavior. Make sense? Okay, now next one. What happened when n is odd but an is negative? N is odd when n is huge positive number, and this part is very, very positive. It's a huge number, and then an is negative, so it kind of like change that to be this, isn't it? And quite opposite on the left side, when x approaches to negative infinity, it goes huge negative number. When x is a huge negative number and x to the nth power, because n is odd, so it's going to be a very, very big, very, very negative number. And then an is also negative, so when you multiply negative an by that very negative, so it becomes this, which means when x goes to the left, keep going and going and going, and then your y or the function value goes great, goes positive. So that's called end behavior of that. All right, now next one, when n is even, that's different. Again, we have an positive and we have an negative. Let's see what happened. When n is even, let's say n is 2, 4, 6, 8, 10, and we put in here, x becomes a huge positive number, and this is a positive. An is positive, so when n gets greater and greater, your y goes greater and greater. And when an is positive, n is even, and then what about the left side? When n approaches to the very negative number, and then to the nth power, n is even. Let's say n is 2 or 4 or 6, so you're going to have a negative times a negative. When n is a 4, you have a negative, 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 negative. So it comes in pairs and it becomes a positive. And your an is positive, so that means when x goes to the left, your y or your function value goes big. I don't know how big it is, but I see the pattern. It looks like that. And when an is even and an is negative, so when x goes to the right, this x to the nth power becomes a huge positive number, and the an is negative, so it drops like that. Okay, and a very similar thinking about this when n is even and you get a negative, but to the nth power, which is going to be positive, but you have an, the leading coefficient is negative, so it goes like this. So this is called end behavior of a polynomial function without knowing exactly what is the value, what the function look like. You can tell by this. Now let me give you a quick example. How do we use this based on what we learned? Now, a student developed a model for the number of Americans with AIDS using the data from 1983 to 2018. You know, some students, when they get the data, or even professor or some other researchers, they get the data, they want to develop a model. So this is the model. F of x equals negative 49x cubed plus 806x squared plus 3,776x plus 2,503. So this is the function or the relationship that he developed. Okay, so x is the number of year, all right, and then the f of x is the number of Americans with AIDS. So I want you to use the end behavior to explain why this model is only appropriate for a limited time period, which means you're not going to be able to use this model forever to make the prediction of the number of Americans with AIDS. So we're going to look at the end behavior, and what we're looking for is we're looking for when x goes to positive infinity. Okay, now what do we have? We have an, in this case is a3, is negative, right? And we have n equals 3, and that's an odd number. Now, odd number here, odd power. So when x becomes a huge positive number, when x keeps going, not only stopped at 2018, let's see, like a million years later. Okay, so this is going to be a million. To the third is also million times a million times a million. I couldn't even know how to say that, but it's huge. But here, this is a negative. So it becomes, I don't really care about those things because this one makes a significant change, much more significant than all the others. That's why when we talk about the end behavior, we only look at the leading term. Okay, so this is positive cube, positive times negative. So our f of x will drop, right? Because it's negative. So eventually it's going to drop below 0, which is impossible. So this degree is odd, and the leading coefficient is negative. So the graph of this function to the right, when x is a very large number, it will be negative, so which is impossible. Okay, make sense? So that means the model the student developed based on the data from 1983 to 2018, this model would work for a certain time period, but not forever. Now you see how I use the end behavior of the polynomial function to understand about this polynomial function. All right, now let's keep going. And there's another concept, it's called a zero. You might say, hey, I know 0, but here this 0 is different than your 0. Okay, your 0 means this, right? Or nothing, or 0. But in this case, we call this as a value of x that makes f of x equals 0, and that is called our 0 or zeros. It could be more. Okay, so 0 of zeros. In another way, it could be just think as the solution of this function, solution of this equation. The value of x that make the function value to be 0. If you graph it, f of x equals 0, that's y, right? So y equals 0, that's the x-axis. So if I have a function, I don't really know the function, but the function looks like this. How many zeros of this function? How many zeros are there for this function? You just need to see how many times this graph will cross or touch my x-axis. So in this case, there are 3 zeros. Is there e? It doesn't matter. So there are 3 zeros for this function. What about this one? There's only 1 0. Okay, there's only 1 0. However, this is, come here, touch, and the leaf is a quadratic. If it's a quadratic, then we're going to say that there is only 1 0, and with multiplicity multiplicity 2. Actually, those are the two zeros. They're just the same. That's what it means. Okay. So this is not too bad, huh? All right, now let's look at this function. F of x equals 1/4 times x plus 2 cube x minus 5 square. This is a polynomial function. What is the degree of this polynomial function? This one, I already put them in this factor format, but if you want to use the distributive property to multiply this out, you should have something look like 1/4, and the highest degree will be x to the third, x to the square second, so it's going to be like this, and all the way, okay? So it's going to look like this. So then, but of course, I don't really need to do that. If you like, you can do it. All right, so how many zeros? There are 2. Remember, 0 is the x value that make this function value to be 0. So many zeros. So x equals -2, x equals 5. So there are 2 solutions to this equation, or we call that there are 2 zeros. Okay, so the zeros are what? A -2 and a 5. We have two zeros. However, did you see this square, this cube? So this is -2 with multiplicity of 2, 3, right? And a 5 with multiplicity 2. Okay. Every time when you hear this multiplicity 3, like a 1, 3, 5, if it's an odd number, it's going to cross the x-axis. If this multiplicity is a 2 or 4 or 6 is an even number, then it's going to just touch. Okay, so that's a little tricky part. You know what the graph of this thing look like? The graph look like this. Okay, so here's a -2 and here's a 5. So it goes like, I couldn't graph it very well. It just go up to somewhere really, really high, and then go down here. It's going to touch. Here's a 5, and here's -2. Here's a 0. That's the graph would look like. Of course, I don't need to do that. I just want to use this to show you. Okay, now after we learned this, see, it's not hard at all, right? We learned what the polynomial function look like. And just by looking at the leading coefficient and the degree, we can tell the end behavior of the graph of that polynomial function. And we learned to identify how many zeros are there. And some zero comes with a multiplicity. And if the multiplicity is even or odd, then it means it's going to touch or cross the x-axis. All right, now next one, important, okay? Every time we talk about a theorem, that's important. It's called an intermediate value theorem. Actually, this is a simple version of the intervalue theorem. Okay, so f of x is a polynomial function with real coefficients, which is, this is a polynomial, and an minus 1 and all the way to a2, a1, a0, they are real numbers. Even some of them are 0, you're missing some term, they're all real numbers. So that means all the term have a real coefficient. All right, if this is the case, and if f of a and f of b have opposite signs, what does that mean? That means one positive, one negative. if this, then there is at least one, there is at least one zero, at least one zero, or we just say at least one value of C, just a lowercase, between A and B, at least one of that, for which f of C equals 0. That means it's going to be at least 1 0 between A and B. What does that mean? Okay, for the polynomial function with all the real number as a coefficient, that graph is a continuous function. Okay, we talk about this later. That's a very different topic. However, that means when you graph it, you can just graph. You can just use your pen to graph it without lifting up. There's no jump, no hole, and no break. Okay, so if you have a function graph looks like, I don't care, okay, it was like that. And if I choose two value, this is f of x. If this is A, this is B. If f of A, see this f of A is negative? It's negative, right? And what about f of B? This is f of B. That's a positive because it's above the x-axis, right? So this is why. Okay. If one negative, one positive, that means your graph is going to cross the x-axis at least once. In this case, it crosses 1, 2, 3 times. Okay, at least once, right? So that's what it says. That means if you go from a point below the x-axis and to another point above the x-axis, then you're going to cross this x-axis at least once. Make sense? Make perfect sense. Or you might have the first one, say A here and a B here. You might have this is positive, this is negative, and then you might have something look like this. So this is a positive, this is negative. They have opposite sign. See, here is that C. We don't need to find out a C. We just need to know there's at least one value between A and B. That is the 0 of this function, or that's a solution of that equation. Okay, now let me give you one example here. All right. Okay, so use the intermediate value theorem. That's using the one we just learned. And I give you the function. F of x equals x cubed minus 2x minus 5. I would like you to use that theorem to show me that this function has a real 0, or at least one real 0, between 2 and 3. Okay. Of course, I'm not going to be able to solve and to find out what is that solution, or what is that 0, but I just need to show that it's between 2 and 3. How do you do that? That will be your A, that will be your B. I need to plug in 2 and 3 into this function and to see whether they have opposite sign. If they do, there's going to be at least 1 0 between 2 and 3. Proved. Okay. If it's not, then forget about that. All right. So let's see what is f of 2. We plug in 2 here, so it's going to be 2 cubed minus 2 times 2 minus 5. So that is 8 minus 4 minus 5, which is negative 1. So that's a negative, okay? And what about f of 3? We plug in 3, so that's the 3 cubed minus 2 times 3 minus 5. That is 3 cubed is 27. Okay, minus 6 minus 5. The answer is 16. So this is negative, this is positive. They do have opposite signs, so there is at least one real 0 between 2 and 3. Proved. Okay? It's because they have the opposite sign. Then that means this. The graph when x equals 2, Here's 1, 2, 3. When x equals 2 is -1, and when x equals 3 is somewhere very up here, so that's a 3, 16. And here is 2, -1. So how do you go from here to here? You have to cross this x-axis somewhere. So that means there is at least one, in this case, there is one real solution or real zero between 2 and 3. Understand? So if I give a function, I give it two values, I want you to show me whether there's any solution between them, then you can go ahead and plug them in, because without solving that is pretty hard. There's no formula for the cube function. Then you can do this way. In computer, if you have a computer, you can write a little program. And what you can do is you plug in x equals 2 and 3. You can easily find out whether they have a negative sign by multiplying these two values to see whether it's negative or not. If it's negative, that means one positive, one negative, right? So next one, you're going to choose the value in the middle, which is 2.5. So you plug in 2.5 in the function to see whether it's a positive or negative. If your 2.5 is a positive, then that means there is a solution between 2 and 2.5. You see what I'm saying here? And if this, when x equals 2.5, you get a negative value, so that means you have the 0 should be between 2.5 and 3. And then if that's the case, then you just chop it in half and then pick this point to see whether the function value of that is positive or negative. By doing this, eventually you're going to approach very, very close to your 0. But that's totally opposite subject. All right, so this is everything you need to know at this moment for the polynomial function.